remember that it's still a conservation energy, so you a volume integration of J dot E, which is the work done to the particles. Right. By substituting the Maxwell equation, you get two terms. Divergence E cos H would be defined as the Poynting vector, that is capital S, and then there are two terms. Right. And to further divide the form, the Poynting theorem that later on we wrote down, we assume the linear medium. So D is epsilon E, and H is P over mu. So that kind of assumption that will allow you to write down the Poynting theorem in integral form would be 6.107, or yeah, and then the differential form is 6.108. Either way, you have the Poynting theorem, and obviously those apply to vacuum because vacuum is obviously a linear medium with a constant dielectric constant and constant permeability. Okay, so and then we actually go back to the vacuum and use the same assumption to divide the Maxwell stress tensor. Okay, so that's 6.7. Now we consider the same equation, but now we make other assumptions, but different from the total linear dependency of E and D. We assume that we consider just a field that is mostly single frequency. The fields is almost all sinusoidal, maybe some slow modulation. So in the Fourier transform, or look at the spectrum of the wave power, so you will center at some omega sub 0, but then the line width will be very narrow. We have a line width delta omega is much smaller than this. But that is in this case. The reason to consider this case is, of course, mathematically, is that allow us to relate D and E without the whole linear assumption, the drastic linear assumption. Basically, look at just a single frequency. In that case, we can look at the Fourier transform of D and E. So Fourier transform of D. And in Jackson, it just changed the dependency. Instead of depends on T, change the depends on omega, but it's different function. You need to be a little careful. Jackson doesn't define another symbol. The Fourier transform now, instead of a constant epsilon, you have an epsilon that depends on omega. Basically, this is the Fourier transform of the dielectric constant. And the Fourier transform of E. Okay, and likewise, you can do the same thing. This is H. Okay. That is more general, obviously more general than the just constant epsilon, constant mu. And in many medium, we will have something similar. And physically, it means something that we'll talk about more in chapter 7. It means that D is not just depends on E. I mean, in not the Fourier transform, the one in the usual time domain, the time dependent D and time dependent E. They are not instantaneously related. That actually D will depend on the integration of E over time, and that is because you multiply by this Fourier transform. Some of you haven't not taking fluid math physics, but this discussion on so-called convolution. It means you need to multiply it, go back to the time domain. That you have an integration of the over E over a certain time. And in chapter 7, we apply the so-called causality to discuss that, because you say it depends on a range of time, but it should not depend on the future of value of E, and that is another story. But we'll wait for that to talk about that. But right now, it's just saying that this is more general. So if you do a free transform, then obviously they can be related linearly, more reasonably related to linearly, unless you are nonlinear terms. So we ignore all the nonlinear, then it should be something like that should happen. And but that is still not obvious. It's still not the most general case. Sometimes it's not just you need to do free transform, not just in the time. You need to do free transform in space also. In that case, that would be a free transform of D in omega, depends on omega, and also what we call the wave number vector of the wave vector. And then epsilon would depend on omega and k also. And that is even more general. But for now, it will just stay with this frequency dependency. And now we can use that and go back to this equation and simplify this as much as we can. And finally, because it's mostly single frequency, we'll take a time average over one period of this corresponding to this frequency, and find another Poynting theorem. And most importantly, the most important physics coming out of this is there's a possibility that there's what we call the dissipation due to the in the Poynting theorem. That now you have an extra term that what we interpret as a dissipation, and that is actually depends on the imaginary part of epsilon. And if epsilon as a function of, I mean, the Fourier transform of epsilon, and if they not just totally real, they have imaginary part, and there is dissipation. Okay, so that is the final goal that we try to get to that. But the derivation to that is a bit long and complicated and require you to understand. I don't know how much you know complex things, or I mean, obviously we have already used all this complex algebra. I don't know whether you. No, we'll see if you stop me if you cannot follow. Okay, it will be a little complicated. So we consider one of the terms. So there's a similarity between these two terms because they are related similarly. We'll consider one of them. Like consider E is the E dot positive D positive T, right? And so let's write it for each one is just like E that depends on X and T, right? And here it depends on X and T still. And then you express it as integral over frequency. That's you have this transform from omega, integrate omega minus infinity to infinity, and we have I think the convention is e to the minus omega t here, and then there's no 2 pi in here. I mean, Jackson sometimes interchange, so he's not using exactly the same convention throughout the book, so you need to be a little careful each time you discuss how you define that. Okay, so that's E, and likewise D will be similar, so that we can write down this one in terms of this E dot also D positive D. This is depends on T. Okay, so that's don't confuse. Sometimes you use the same symbol that sometimes there will be some confusion, and you substitute this into here, but then we expected there's two omega because these have the same integral form like this. So that is integral of omega. So you cannot use the same omega in two integral, otherwise it's too confusing. So we can change this like e, we use omega pi instead of omega. Okay, e x omega pi. It's just the same thing. It's just an integrated variable, but that just to avoid confusion. Okay, and then you dot into something similar to here. But then you take the derivative, and when you take the derivative only act on this exponential function, and the result is just multiplied by minus I, because derivative of exponential function is itself, and then you take the derivative over the argument. In this case, you will pull out my factor minus I. So you have minus I and the same thing. Now it's omega instead of omega pi, and then you have e to the minus I omega. Okay, I think it's not quite Jackson's expression. Jackson's expression is in order to get to Jackson's expression, you actually do a change of variable, and then use a result that we'll talk about a little bit later. So basically, you change omega pi to negative. Basically, reverse the sign of the omega pi and change the minus omega pi. Okay. So do this operation. So instead of writing another line, I'll be a little lazy. So work on this thing. Just change the omega pi and change the omega. So basically get rid of this negative sign. Okay. And then for the integral, we first change the minus. This is minus omega pi. And for the integration, that becomes minus d omega pi. But then the integration limit will change to positive infinity to negative infinity, right? And then now the final step, we use the negative sign to flip the sign. You flip the sign, you introduce a negative sign, and you cancel this negative sign. Basically cancel that and change back to minus infinity. Okay. Okay. So all this is just doing this substitution, a change of variable. But the only thing now is that E now has the argument depends on minus or pi. And now we use the fact that E is a real expression. Okay. And if E is real, then it should equals to E compact conjugate, right? You know what I'm saying? So I just not sure you are familiar with all this complex thing. This you can agree with the complex. And then the complex conjugate of E is just using exactly the same expression, and then doing complex conjugate of each part of the expression. So E x omega change E complex conjugate x omega. And then for this part, you just explicitly changing I to minus E. Right? And now you do the same trick, changing omega to minus omega. And all you do is change this to minus, change this to minus. And this doesn't change just like what we did. Change the minus here, you change the limit. But then you flip the limit to get rid of the negative sign. Okay, now you compare this with that, because this equals to that, and both have the same form. including the exponential function. So it must means that this part equals to that part. So it means E x omega E complex conjugate x minus omega. Or if you want to use this, you put the negative sign here, and this becomes positive. Okay, and we have something like that here, right? So this is just like that. So you can get rid of this negative sign in the argument by taking something. Okay, there's a lot of this complex manipulation, and I mean this is basically just an exercise, but this is important. Whenever you have a real quantity, and then the complex conjugate of its Fourier transform is the same as you're taking the negative frequency, evaluate a Fourier transform using negative frequency. But this is a general, so not just for the electric field. We just use the fact that we assume that the electric field is real. So it equals to its own complex conjugate, and you have this result. So the negative frequency is equal to just taking the complex conjugate. Okay. So now you get to this part. This is Jackson. I forgot. Jackson is not done yet the argument. So the final expression is just changing d to using that what we talk about that before epsilon omega e. Okay. So now you have everything. Yeah, this is epsilon. That's too many brackets. Epsilon divided omega. So this is the equation at the bottom of 262. And okay. Now the trick specified by Jackson is just do the same thing instead of this is omega, this part E, the first part is omega pi, the second part is omega. You're basically calling omega pi to negative omega and omega to negative omega pi. Okay. Well, calling omega and omega pi is just fine. You can do it step by step, right? If you just do, I mean that would be easier, less confusing, because omega and omega pi are just integration variable. You can call them whatever you want. And now we call omega omega pi omega, and then omega pi, and that is easy. So we change the omega. Complex conjugate x omega e to the I omega t, and that becomes minus I omega pi, and this is epsilon omega pi e x omega pi e to the minus I omega pi t. Right, that is easy. Now we do the same trick. I forgot this. This is another integral. This is the integration. Yeah, I mean we could actually put everything to the beginning. So there's the omega. Well, you exchange omega and omega pi, that doesn't matter. Okay. Now the idea is to go back to something similar to this one. But this is that omega pi has a positive sign, omega pi here is negative sign, and likewise, this is minus I omega t, this is I omega t. So the next step is to change omega to minus omega and omega pi to minus omega pi, just like what we did before, right? And now, again, we do just the trick here, just minus, this become plus, the argument is minus, this I omega pi become plus, and this is minus, this is minus. And all the integration thing doesn't change because we've done that a few times now. Change the minus sign and flip the sign, and they use the minus sign to flip the sign again. Okay, so this doesn't change. And the final step is using this expression, I mean this relation. The negative frequency evaluation is just like doing a complex conjugate and get rid of the negative frequency and positive frequency. So we can do that for this one. You can get rid of that and take the complex conjugate. And this one, I think we do the same thing, get rid of that. Get rid of the negative frequency because epsilon is also a real quantity. And likewise, you change, get rid of the negative sign and do a complex conjugate on the complex conjugate, which is reverse to the original one. Okay, so that is this one is just equals to that. Now this one is very similar to that. So you have E and then E complex conjugate on omega pi. And this is similar to that. This is similar to that. Everything is the same except this is a minus I omega. This is I omega. Okay, so this is different. And then the epsilon is also different. Epsilon is also different. Okay. So except this one is the same. The final step is because they are the same, you can add the two and divide it by, multiply by 1/2. That is still the same. So, yeah. And then let's write it like Jackson. So we have E complex conjugate x omega pi dot into now the difference part you have to this to add together. I think Jackson wrote it like a one. Yeah, just copy it here. So one side omega epsilon omega plus A omega pi x complex conjugate omega pi. This is dot into E omega. And now you have exponential function and Poynting Jackson is minus I omega minus I. Okay, so that is 6.124. Now the crucial approximation is that just like what we wrote, we draw in the diagram, the spectrum is mostly single frequency. So I think it's called omega sub 0. I mean, actually, it doesn't need that. Later, it's called omega sub 0. That's what. But in this integram, it depends on omega and omega prime, but they will be 0 if they are not within this range. Outside, if omega or omega prime outside this range, the whole thing is 0. So, so that doesn't contribute to the integral. So you only need the part that is non-zero. And when they are both within this range, so omega is here, omega prime is here, then you can do a Taylor expansion of this function. And in particular, I think omega express epsilon pi. So I mean, this epsilon based on this picture. So work on this. the Taylor expansion epsilon omega prime would be like epsilon omega plus d epsilon d omega, but then evaluate omega and then multiply by omega prime. Right, that's the Taylor expansion. And then we keep just the linear term and then ignore all the high order term. Then we can substitute this into here, right? Because this obviously you take the complex conjugation. Complex conjugate. Right. Now you substitute this into here. That just consider the square bracket. We have minus. The first term is we have minus I only. I mean, there's a omega here also. But omega, because both are first close to here, omega sub 0. So in this term, we actually just keep omega pi. Just the omega pi is very close to omega anyway. So for the first term, we have epsilon complex conjugate in here, and then both are similar, and it basically is the quantity plus its complex conjugate. So basically, what you get is the imaginary part. So, so any quantity A plus the complex conjugate is 2 times 2I times imaginary. Is it familiar to you? Any quantity plus its complex conjugate is 2 of the. It's, this is right, right? You accept that? You haven't. No, I have not. Yeah, so it's just like you write A like A equals to A real plus I A. Yeah. A complex conjugate A or minus I. And they subtract the 2, and then actually I said it wrong. Minus A minus this one. So that's actually this one. If you minus that, then this cancel, then that would be 2 of the I, imaginary part of 2 I base of I. If you add that, you will get actually 2 of the real part. But in this case, you actually subtract them, because after you substitute this in here and you approximate omega pi equals omega, and that will give you 2I, but then you already have an I. So 2I actually have a minus I because you just subtracted that. You subtract by that. So you have 2I, I cancel because I times minus I is 1. So you have 2 of imaginary. So that was and multiply by omega as well. Omega is real, but you can take it out of the imaginary. But Jackson write it like that. Write it again. Omega times epsilon omega. But that is the first term. And then the second term would be, because you already canceled that, you have you just have this one and multiply by I plus I omega pi minus omega. T epsilon complex quantity omega. Oh, there's an omega pi also. Yeah. Oh, I see what I did. I see what I did. Actually, the Taylor expansion is not just over, not just over epsilon. You're basically writing omega. That becomes omega. And this is actually the omega epsilon. Wait, that is that that with this one substituted in this one will give you this one automatically because you're already assuming that this is omega pi is the first term is this omega and there's omega also. So you don't actually need to do this approximation. And then you get two imaginary part of this one. But omega is anything anyway. So the stability is over omega times epsilon omega epsilon complex quantity omega. Okay, that's more like it. And this is important because the final form depends on exactly this one. So let's clean it up and write it up here. So this is equals to that. Yeah, this is write it out. Dot space dot positive. I have electron. So this is 1/2 and double integral. There's just a few steps left. Then we have E. Dot, the first term, just this term is this E complex conjugate. It's omega A dot and the E. It's omega. So basically this one and this one. And then you have this two imaginary epsilon and omega. And this two cancel with the 1/2. With the 1/2. And you have this omega can be taken out out of this imaginary of the imaginary. And finally would be this space factor. Okay, so that's the first term. Now the second term has a trick also, because you have minus I omega pi minus omega, and or you can change it. This omega pi minus omega is changed to omega minus omega pi, negative sign here. You see that this is the same factor as in front of t of the exponential factor. So you can absorb this into the exponential factor by changing this t ddt or partial t. Inside the integram is ddt partial t, but the outside of the integram will be ddt. Oh, but I think you can keep using partial t, right? If you get rid of this minus I omega minus omega pi, or you need this, just do it. Derivative over t, because that operate on this one will pull out this factor. Okay, so the other one is partial t of 1/2. Same thing. And factor is, instead of this imaginary one, you have this dd omega. Okay. omega times x complex conjugate. And the rest is the same exponential factor. This is omega. Yeah, this is. Okay, so this is 6.1 25. Okay, and now the same happens. You can do the same thing for h dot partial b partial t, but obviously you don't need to repeat all the math because everything is just the same except that you change whenever you see E, you change it to H. Whenever you see D, you change to B. But D and D is epsilon E, B is mu H. So the epsilon will change to mu, right? So if you want to do it more explicitly, so if you change it to H dot partial B partial T for this term, all you need to do E will be all H, this will be H, this will be H. And epsilon becomes mu, and this will be H, this will be mu. And then you add the two. Okay, so this is this two is getting into here. And the final step is this is over a single, I mean, the wave is almost single frequency. Then it might be better to just consider the time average quantity over one period. So that is this square bracket operation. So basically, you want to do a square bracket over these two terms, and for these terms are, you can say that some of them is just will give you a single frequency. Say if you assume epsilon doesn't change, so you have this epsilon that change slowly over this width. Then whenever you see epsilon, this dielectric constant epsilon, although it depends on frequency, but it depends on frequency much more slowly with unlike this sharp spectral line for the field. Then whenever you see epsilon, you can just evaluate that at epsilon zero. It is evaluate at epsilon zero. After you do the derivative, you evaluate at epsilon zero. I mean, not epsilon, omega sub zero. Everything at omega sub zero. And this one also. This omega obviously changing slowly. It's just a function, just a linear function. And change that to omega sub zero. Okay, and then you recognize this is nothing but just the Fourier transform of E dot in the Fourier transform of itself, the compact conjugate, or you can just do the evaluation. This is just like what we call the inverse Fourier transform. So this, like the E omega, you use the minus I omega t, the d omega, that will give you back the E x t. Remember that it's ext. It's just E omega x omega minus I omega. Right? You will change that. It doesn't depend on this. Taking these out of the integral. With this integrate over this one, and this factor will give you just this one. And likewise, the convex conjugate will be just this is just like the complex conjugate will be this complex conjugate changing to positive sign. But E actually is real, so it doesn't matter. So it will be just this one integrated the omega pi and this second exponential factor. So this will be just like a E dot E. So this is just E dot E. But you know you're taking the time average. The F of E dot constant. So let me just write down this 6.126 positive D positive T. So H dot positive D positive T. Basically add the two. The first term is basically add the two, and now you have to pull this out, omega sub 0 are imaginary omega sub 0, and then you average over E dot E. Now this is all dependent x and t over one period of time. This is just average, and assuming E just moving slowly, and then the omega sub 0. Now it's changed to mu omega sub 0, or imaginary mu sub 0. Mu equivalent omega of 0, and then h dot h. These are in the time domain, not compact quantity. Okay, and then finally you have the second term, so partial t, and you could do the same thing, so multiply all this out. Technically, all evaluate omega sub 0, take that out, and the rest is just 1/2 of this, whatever you pull that out. So this is omega epsilon, and you have omega mu complex conjugate, and finally you have the same thing. Actually, you just one need to multiply by e. You need to multiply by x. And finally, we define that as the energy density. Okay, that would be 6126b. And combine that, that's you get the 6126b. Okay, so our time, but that's a lot of manipulation and complex. Hopefully, I mean, if you forget everything, you just remember how to do this complex manipulation. Okay. Microscopic form of the conservation of energy is 6.126.8 or Poynting's theorem. So the one thing that is more than what we had in the 6.7 is the first two terms. Those are the dissipation terms. So you write it down. So you got both the electric field and magnetic field terms. So you have two parts. So although you average over time, but you still have time left. The time is so-called slow time because you average over the frequency, but it's not a single frequency. It's like way that mostly sinusoidal, but it has a slow. So this is in time, right? It has slow profile. It still depends on time, but depends on the slow time after you average over the one period of time. It is about one period. And that is what is left. And the first two terms are the dissipating term. You have omega sub 0, the imaginary part of the epsilon. So the dielectric constant, it turns out that there will be imaginary part, and that is unavoidable except for vacuum. And we'll talk about that in chapter 7. And the average over the E square, basically E square. And similarly, you have the imaginary part of the permeability. And then the final term is like the time derivative of the energy density. But this time derivative, after you do the time average over the shorter period of the almost single frequency, this is the slow modulation. And you have this effective energy density. That the form of the effective energy density is from the second term in 6125, right? But you take the real part. You take the real part because we already talked about that. All the complex treatment is basically you're using complex notation, but eventually you will take the real part for your physical result because when you measure it, you measure something real, and the time average of the energy obviously is a real quantity. So you are taking the real part of the second term in 6125, and so that is. And again, in 6125, you have the dd omega and then omega epsilon complex conjugate. And that one is slowly moving in time. And I mean, slowly moving in frequency, actually. It's not single frequency. So you can evaluate that in the single frequency omega sub zero. So basically, you substitute the omega sub zero. You have omega sub zero. Yeah. You actually take the dd omega and omega epsilon, which also depends on omega, but you multiply by another omega and then that evaluate that and take the real part. And the rest is just that's the same as this one. This one actually is supposedly is complex conjugate times. But, one of them is the complex conjugate. But Jackson didn't have that notation because originally E is I mean this you assume E is initially is real, then you don't need to take the complex conjugate. But from the mathematical formula from 6127, that term is complex conjugate. But eventually you assume the field is real, right? But that from the electric field, and then the magnetic field is just the same. The substitution is omega mu complex conjugate. Jackson also didn't write down the complex conjugate, but you actually need that. Although you take the real part, everything else is complex. Not I mean the only complex part is epsilon. So whether you take the real part of epsilon or the real part of epsilon complex conjugate will be the same. The real part doesn't change, but you take the complex conjugate. Jackson ignored this one. Originally, there's a complex conjugate. All right, so that is the Poynting theorem in microscopic form. No, not quite. This is this is just the two terms. Then you still need the J dot E term. The next line 6127. You add back the J dot E term and the divergence S term. That would be the Poynting theorem. So 126 is just the other two terms in what we left in 127, which is 6105. The last two terms after you take the average is 126, and you put back to the equation, you get 6127. That would be the Poynting theorem. Okay, so that's the new thing in this Jackson called the dispersive medium, because if you have this epsilon that depends on omega, so that's what we call the dispersive medium. If epsilon actually doesn't depend on omega, then that becomes a constant. Then this dd omega is just nothing. Just can basically just give you one. That becomes epsilon e squared. This is like b dot e. This would like b dot h. So that would be exactly the same as before. What we call the non-dispersive medium. That is in 6.7. The expression would be the same, right? And obviously that is microscopic. You can also do it volume integral and get the macroscopic energy conservation law.
So when we are finding the time average of E dot E, should we do the integration like finding an expectation value?
This one?
Yeah.
This one is originated from the
how do we find time minus infinity?
The time is defined as actually so whatever quantity, this is defined as 1 over the period over. So the period is 2 pi over omega. 2 pi over omega sub 0. Okay, and that can you integrate whatever the quantity dt, and you can or dt pi, and from any time t to t plus the period t, 2 pi over omega sub 0. Right. That is usually that is what is defined as the time average. But this quantity, like again, is it's not totally single frequency. It has some modulation of the single frequency. So even if you are integrating over one period, it still depends on time. So whatever time it is, so that is a slow time dependent. So this is still a function of time through this t. That's whatever the quantity is, say like an average of an electric field. Now this is T pi. T pi include all the fast oscillation, almost single frequency oscillation. But once you integrate that over, what is left is this modulation. So that's still dependent. Okay, and that would go into this time period, because you all average that the fast time is average out over these two terms, but you still have this slow time through this the integram. So that will go into this period. Okay, yeah, and Jackson has this kind of model using like this. If you want, you can use Jackson's model. Say this is the electric field is something like there's a slow time dependence. This E tilde. It's actually a vector and then tilde. This is another symbol, and then this is the fast time oscillation, like a sinusoidal one. CT plus alpha. And if just getting phase factor instead of writing it two terms sine and cosine. Okay, and then you can do this kind of time average and convince yourself that that is you get the the equation in 6126. Right. Okay. So for this section, the main physics coming out is that you can generalize 6.7, which is a constant epsilon, constant mu, to a medium that doesn't satisfy that. But instead, each frequency has its own dielectric constant and the permeability. So instead of the D is epsilon E that you usually assume, then actually this relationship actually is satisfied through the Fourier transform. So everything in the omega space, right? And likewise for the magnetic field. So that the first generalization, and then you can write down the energy conservation of this kind of medium, the dispersive medium. And one thing coming out is that for dispersive medium, there's a possibility for dissipation term for some frequency, at least. So this would depend on frequency, but for a frequency, whether there's exception depends exactly the property of epsilon and mu. So it's not always have dissipation for any frequency, but overall frequency, there will be some ranges of frequency that you will have dissipation. So that is something new, and but then you can obviously you can still have a conservation of energy, and so but that conservation to the Poynting theorem will have the dissipation term. Okay.